Heavy machinery is built to embody confidence, power, durability, and engineering authority. But history shows that a single machine, when it fails at the wrong moment, can do far more than break down in the field. It can fracture trust, drain capital, and expose weaknesses executives never intended the public to see. This story is not about small defects or routine recalls. It is about bold machines launched under pressure, rushed innovations sold as breakthroughs, and designs defended long after warning signs appeared. In boardrooms and job sites alike, these machines triggered lawsuits, accelerated collapses, and reshaped entire companies. What follows is a look at 12 heavy machines that did more than disappoint customers. They changed corporate trajectories, sometimes irreversibly, and proved that in this industry, failure rarely stays mechanical. Caterpillar L10 engine, the lawsuit that cost billions. Caterpillar's L10 diesel engine was introduced in the late 1970s as a breakthrough power plant for heavy trucks, construction equipment, and industrial applications. It was marketed as lighter, more efficient, and technologically advanced compared to earlier Caterpillar engines. For a company built on durability and trust, the L10 was supposed to reinforce Caterpillar's dominance. Instead, it became one of the most damaging engineering decisions in the company's history. In an effort to reduce weight and improve fuel economy, Caterpillar redesigned internal components using lighter materials and thinner tolerances. These choices looked sound on paper, but proved vulnerable under real-world operating conditions. Across the United States, L10 engines began suffering from premature failures. Crankshafts cracked, bearings failed, and blocks experienced structural fatigue far earlier than expected. Long-haul truck operators reported breakdowns at mileages that should have been routine. What made the situation explosive was not just mechanical failure, but Caterpillar's response. For years, the company denied that a systemic defect existed. Warranty claims were contested, repairs were delayed, and customers were often blamed for improper maintenance. By the mid-1980s, frustration turned into legal action. Fleet owners accused Caterpillar of knowingly selling defective engines while concealing internal test data. Internal documents later revealed that engineers had warned management about durability risks before mass production. The lawsuits escalated into one of the largest product liability battles in heavy machinery history. Caterpillar eventually settled multiple class action cases, paying hundreds of millions of dollars in compensation and repairs. Additional costs came from engine replacements, warranty extensions, and lost sales. The financial damage went far beyond settlements. The L10 crisis weakened Caterpillar's reputation at a time when competition from Cummins and foreign manufacturers was intensifying. Customers who once viewed Caterpillar as unbreakable began questioning its engineering judgment. Internally, the episode forced painful changes. Caterpillar revised its testing standards, strengthened quality oversight, and became more cautious about aggressive redesigns. But the damage was already done. The L10 did not bankrupt Caterpillar, but it permanently altered the company's trajectory. It demonstrated that even industry giants could be undone by a single, flawed product. More importantly, it showed how denial can multiply engineering mistakes into corporate disasters. Years later, the L10 remains a cautionary tale taught in engineering and business circles. The engine was not remembered for innovation, but for the cost of ignoring early warnings. In heavy machinery, failure is rarely sudden. It is often denied until it becomes irreversible. For Caterpillar, the L10 lawsuits marked a turning point between unquestioned authority and public accountability. Trust, once lost, proved far more expensive than any redesign. The engine that was meant to secure dominance instead exposed vulnerability. In the end, the L10 did not just fail mechanically, it failed strategically, legally, and culturally. That combination turned an engineering problem into a billion-dollar lesson the industry could not ignore. The case remains one of the clearest examples of how a single machine can damage even the strongest corporation. It stands as a reminder that reputation is built slowly and destroyed far faster. International Harvester, Payline excavators, the gamble that accelerated collapse. International Harvester entered the 1970s already under strain. Once a dominant force in agricultural equipment and trucks, the company was losing ground to more specialized competitors in construction machinery. In an effort to regain relevance, International Harvester placed a major bet on its Payline excavator series. Introduced as a modern, competitive answer to machines from Caterpillar, Komatsu, and emerging European brands. The Payline excavators were ambitious by design. They were intended to offer strong digging power, advanced hydraulics, and versatility across mining, construction, and infrastructure projects. On paper, the machines looked capable. In practice, they exposed the limits of International Harvester's fragmented engineering and overstretched resources. From the beginning, reliability issues plagued the Payline line. Hydraulic systems were inconsistent, suffering from leaks, pressure instability, and premature seal failure. Swing motors and pumps showed accelerated wear, especially under continuous duty cycles common on large job sites. Electrical systems, already a weak point in many International Harvester products, proved vulnerable to vibration and heat. Operators reported frequent downtime, often for problems that competing excavators had already solved. Repairs were time-consuming, parts availability was uneven, and service documentation lagged behind real-world needs. Contractors who adopted Payline machines expecting competitive performance instead found themselves absorbing lost productivity. The deeper problem was financial. Developing the Payline excavators required massive capital investment at a time when International Harvester was already struggling with declining profits, labor disputes, and mounting debt. Instead of stabilizing the construction division, the excavators became a cash drain. Warranty claims grew faster than sales, eroding margins almost immediately. Management's response worsened the damage. Rather than pausing production or redesigning core systems, International Harvester continued pushing Payline machines into the market. Sales teams were pressured to move inventory, even as internal reports highlighted persistent reliability complaints. The company could not afford a full retreat, and that inability trapped it deeper. By the late 1970s, competitors exploited the situation. Contractors who experienced Payline failures shifted loyalty to Caterpillar, Komatsu, and Hitachi, often permanently. The Payline name, intended to signal progress, became associated with risk. That reputational damage spread beyond excavators, reinforcing doubts about International Harvester's broader engineering discipline. The Payline program also diverted attention from other critical problems. Resources that could have supported core agricultural and truck operations were instead tied up in defending a struggling construction line. As losses accumulated, confidence from investors and lenders weakened further. When International Harvester began dismantling and selling off divisions in the early 1980s, the Payline excavators stood as a symbol of overreach. They were not the sole cause of collapse, but they accelerated it. The machines arrived at the worst possible moment, magnifying existing weaknesses rather than correcting them. In hindsight, the Payline gamble revealed a fatal miscalculation. International Harvester attempted to fight specialized competitors without the organizational focus or financial stability required to win. The excavators did not just fail in the field, they failed strategically. The Payline story illustrates how a flawed product, launched at the wrong time, can become an accelerant rather than a solution. For International Harvester, the excavators meant to secure a future, instead helped hasten the end of an era. Komatsu D575A prototype overreach, when bigger became a liability. Komatsu's D575A bulldozer began as an audacious statement. Developed in the late 1980s and refined through the early 1990s, it was designed to be the largest operational bulldozer ever built. With a weight exceeding 140 tons and an engine producing over 1,000 horsepower, the D575A was intended to dominate large-scale mining and earth-moving projects where shear force promised unmatched productivity. From an engineering standpoint, the machine was extraordinary. Its blade capacity dwarfed anything in its class, and in controlled conditions it could move volumes of material no conventional dozer could approach. For Komatsu, the D575A was meant to demonstrate technical supremacy and challenge Caterpillar's symbolic dominance in large earth-moving equipment. But size introduced problems that power could not solve. The first issue was logistics. Transporting the D575A required full disassembly into multiple sections, special permits, and weeks of preparation. For many mining operators, the cost and time required just to move the machine to a site erased much of its productivity advantage before it ever touched the ground. Operational flexibility was another weakness. The D575A was effective only in very specific environments. Open pit mines with vast, unobstructed working areas. On tighter sites, the machine was inefficient, difficult to maneuver, and underutilized. Its immense blade was an asset only when conditions were ideal. Maintenance proved equally challenging. Specialized parts, unique systems, and extreme component loads increased service complexity. Downtime was costly, and repairs required technicians with rare expertise. For operators accustomed to fleets of standardized machines, the D575A became a logistical outlier rather than a workhorse. The financial implications quickly became clear. The bulldozer's purchase price was enormous, but ownership costs were even higher. Fuel consumption was extreme, and utilization rates rarely matched projections. Mines that bought the machine often discovered it spent long periods idle, waiting for conditions where its full capability could be justified. Internally, the project strained Komatsu as well. Development costs were high, production volumes were low, and economies of scale never materialized. The D575A functioned more as a custom-built spectacle than a sustainable product line. While it drew attention in headlines, it failed to generate proportional returns. Critically, the machine highlighted a strategic miscalculation. The industry was moving toward flexibility, efficiency, and optimized fleet integration, not singular, ultra-specialized giants. Komatsu's competitors focused on scalable solutions that could be deployed across varied sites. The D575A went in the opposite direction. By the late 1990s, Komatsu quietly limited production and shifted focus away from extreme-scale machines. The D575A was not a technical failure, but it was a commercial one. Its existence proved that engineering achievement does not guarantee market success. The bulldozer became a cautionary example within the industry. Bigger did not mean better if that size reduced adaptability, inflated costs, and narrowed the customer base. The D575A showed how overreach, however impressive, can turn innovation into liability. For Komatsu, the lesson was expensive but clarifying. Dominance in heavy machinery would not be won by extremes alone, but by machines that balanced power with practicality. The D575A remains a symbol of ambition unchecked by market reality. Detroit Diesel Series, 60 early emissions models, compliance that backfired. When Detroit Diesel introduced the Series 60 in the late 1980s, it was widely regarded as a technological leap forward. It was the first heavy-duty diesel engine to rely fully on electronic controls, promising improved fuel efficiency, diagnostics, and emissions management. For Detroit Diesel, the Series 60 was not just a product. It was a strategic pivot meant to secure relevance in an industry facing tightening environmental regulations. That strategy became risky in the early 1990s, when new emissions standards forced rapid changes. To comply, Detroit Diesel implemented early emissions control calibrations that prioritized regulatory targets over long-term durability. On paper, the engines met requirements. In real-world operation, the compromises quickly surfaced. Operators began reporting drivability issues, inconsistent throttle response, and premature component wear. Electronic control modules, still relatively new to heavy trucking, proved sensitive to heat, vibration, and electrical noise. Sensors failed more often than expected, triggering limp modes that sidelined trucks unexpectedly. For fleets built around uptime, these interruptions were costly. Cooling and combustion tuning also became problematic. To reduce emissions, early Series 60 models ran hotter and relied on tighter tolerances. This increased thermal stress on injectors, valves, and turbochargers. While catastrophic failures were not universal, the frequency of repairs exceeded expectations, especially in high-mileage applications. What turned engineering strain into corporate damage was perception. Detroit Diesel had marketed the Series 60 as the future of reliability through electronics. When problems emerged, customers felt misled. Fleet managers accustomed to mechanical engines viewed the new systems as fragile and opaque. Troubleshooting required specialized tools and training that many service centers lacked. Competitors exploited the moment. Cummins and Caterpillar emphasized proven durability and gradual emissions transitions, positioning Detroit Diesel as an example of a technology introduced too quickly. Fleets delayed purchases or shifted suppliers entirely, eroding Detroit Diesel's market share at a critical time. Internally, the cost mounted. Warranty claims increased sharply, forcing Detroit Diesel to absorb repair expenses and issue updates. Engineering teams worked to refine software, improve component resilience, and stabilize operating temperatures. These fixes eventually improved the Series 60's reputation, but not before significant damage had been done. The financial impact extended beyond direct costs. Trust loss meant lost contracts, particularly among large fleets wary of regulatory-driven experimentation. Detroit Diesel's parent organizations were forced to reassess product rollout strategies, slowing innovation to rebuild confidence. The Series 60 survived, but its early emissions phase left scars. The episode demonstrated a harsh reality of heavy machinery development. Regulatory compliance can become a liability when it outruns field readiness. Detroit Diesel met the letter of emissions law, but underestimated the operational consequences of rapid change. In hindsight, the early emissions Series 60 models were not a failure of concept, but of timing. The technology itself would later become industry standard. Introduced too aggressively, however, it backfired, turning compliance into controversy and innovation into a reputational setback. For Detroit Diesel, the lesson was expensive. Meeting regulations is mandatory, but maintaining trust is existential. When compliance compromises reliability, the cost is paid not just in repairs, but in customers who never return. John Deere 8440 Tractor. Power without reliability. When John Deere released the 8440 tractor in the late 1970s, it was meant to represent a new tier of agricultural power. Part of Deere's ambitious 40 series, the 8440, was designed as a high-horsepower four-wheel drive tractor, capable of handling the largest implements on expanding North American farms. On paper, it delivered exactly what farmers wanted: size, torque, and brute pulling ability. In practice, the 8440 quickly gained a reputation for something far more damaging: unreliability. The tractor's problems centered on its drivetrain and powertrain integration. The 8440 used a complex transmission and final drive system that struggled under sustained heavy loads. Farmers reported frequent failures in differentials, axles, and transmission components, particularly during deep tillage and continuous field work. These were not edge cases. They occurred during normal use, often well within expected service life. Hydraulic issues compounded the problem. The system was powerful but inconsistent, with reports of pressure loss, overheating, and erratic response. For operators running large planters or heavy implements, hydraulic instability translated directly into downtime and lost productivity during narrow planting and harvesting windows. What made the situation worse was timing. During the late 1970s and early 1980s, farm economics were tightening. Rising interest rates and volatile commodity prices left farmers with little tolerance for expensive breakdowns. The 8440 was not just costly to purchase, it was costly to keep running. Repairs were complex, parts were expensive, and downtime could not easily be absorbed. John Deere's response struggled to contain the damage. While the service bulletins and component updates were issued, many farmers felt the fixes arrived too late or failed to address root causes. Some machines required repeated major repairs, eroding confidence not only in the 8440 but in Deere's high horsepower lineup as a whole. The reputational impact was severe. Farmers who had long viewed John Deere as the gold standard for reliability began reconsidering brand loyalty. Competitors such as Case and International Harvester seized the opportunity, promoting simpler, more robust designs that emphasized durability over peak specifications. Financially, the 8440 became a liability. Warranty claims mounted. Resale values fell, and unsold inventory lingered on dealer lots. The tractor did not destroy John Deere as a company, but it inflicted real damage during a period when the agricultural equipment industry was already under stress. Internally, the failure forced reflection. Deere engineers reassessed drivetrain design, testing protocols, and the risks of scaling power too quickly without sufficient field validation. Later models incorporated stronger components and more conservative engineering choices, but those improvements came after trust had been shaken. The 8440 stands as a cautionary example of how power alone cannot define success. Farmers needed machines that worked every day, not just impressive specifications on a brochure. When reliability fails, horsepower becomes irrelevant. For John Deere, the 8440 was a painful lesson. Engineering ambition must be matched by durability in the field. Without that balance, even a powerful machine can undermine the very reputation it was meant to strengthen. Terex Titan, 797 prototype, engineering spectacle, commercial failure. When Terex unveiled the Titan haul truck in 1974, it was intended to redefine what heavy mining equipment could be. Officially designated the Terex 3319 Titan, the machine was the largest off-highway haul truck ever built at the time, dwarfing anything operating in open-pit mines. Weighing more than 500 tons, fully loaded, and powered by a massive diesel-electric system, the Titan was conceived as a technological statement: bigger capacity, fewer trips, and unprecedented productivity. From an engineering standpoint, the Titan was extraordinary. Its diesel-electric drive, inspired by locomotive technology, delivered immense torque and allowed the truck to haul payloads exceeding 350 tons. The machine stood nearly as tall as a three-story building, with the tires over 11 feet in diameter. For Terex, the Titan was meant to showcase innovation and position the company as a dominant force in ultra-class mining equipment. Commercially, however, the Titan was a disaster. The core problem was practicality. Very few mines in the 1970s were designed to accommodate a vehicle of such extreme size. Haul roads required extensive widening and reinforcement. Maintenance infrastructure had to be custom-built. Even routine servicing became a logistical challenge, often requiring cranes and specialized crews. The theoretical efficiency gains of moving more material per trip were quickly offset by operational complexity. Reliability further undermined the concept. While the diesel-electric drive was powerful, it introduced layers of electrical and mechanical complexity unfamiliar to many mining operators at the time. Downtime was costly, and diagnosing failures on a one-of-a-kind machine was slow and expensive. With no fleet redundancy, any breakdown effectively sidelined the entire experiment. Economic conditions made matters worse. The global mining industry entered a downturn in the late 1970s, reducing capital spending and appetite for risk. Mining companies that might have considered ultra-large trucks instead opted for proven, scalable fleets of smaller haul trucks that offered flexibility and redundancy. A single Titan represented too much concentrated risk. For Terex, the financial consequences were severe. The Titan was never mass-produced. Only one operational unit was built, and it failed to generate follow-on orders. The immense development costs could not be recovered, and the project strained a company already facing broader financial challenges. Instead of establishing Terex as an industry leader, the Titan became a symbol of overreach. The contrast with later developments is telling. Decades later, Caterpillar's 797 series, ironically sharing a similar numerical designation, would succeed by pairing extreme payloads with modular support, global service networks, and mines designed specifically for ultra-class trucks. Terex lacked that ecosystem in the 1970s. Today, the Titan survives as a museum exhibit, admired for its ambition and scale. It remains an engineering landmark, but also a warning. Innovation untethered from market readiness can become a liability rather than an advantage. The Terex Titan did not fail because it was poorly engineered. It failed because it arrived too early, too large, and too impractical. As a commercial product, it stands as a reminder that spectacle alone cannot sustain a company in an industry governed by economics, reliability, and real-world constraints. GM Electromotive SD90M-AC, the locomotive that customers rejected. When General Motors' Electromotive Division, EMD, introduced the SD90M-AC in the mid-1990s, it was intended to secure the future of American locomotive dominance. Railroads were demanding more power, lower operating costs, and compliance with tightening emissions standards. The SD90M-AC was pitched as the answer, a next-generation, ultra-high horsepower locomotive designed to outperform anything on North American rails. Instead, it became one of the most expensive miscalculations in modern railroad manufacturing. At the heart of the SD90M-AC was the experimental H engine, a massive 16-cylinder, 4-stroke diesel designed to produce 6,000 horsepower, far more than the industry-standard 4,000 to 4,400 horsepower locomotives of the time. On paper, the concept was compelling. Fewer locomotives per train promised fuel savings, reduced crew requirements, and higher productivity. In reality, the H engine was not ready. The engine suffered from chronic reliability issues almost immediately. Railroads reported excessive vibration, overheating, oil consumption problems, and premature component wear. Maintenance crews, accustomed to decades of experience with EMD's proven two-stroke 710 engines, struggled to service the unfamiliar design. Downtime increased sharply, erasing any theoretical efficiency gains. Compounding the problem was EMD's decision to sell many SD90 MAC units in a convertible configuration. These locomotives were delivered with a derated engine and the promise of a future upgrade to the full 6,000 horsepower H engine once development issues were resolved. That upgrade never materialized as planned. Railroads were left with oversized, overweight locomotives that delivered no real advantage over existing models. The SD90 MAC also arrived at the wrong moment economically. During the late 1990s, railroads prioritized reliability, fleet commonality, and life cycle cost control. The SD90MAC failed on all three fronts. Its unique components limited parts availability, training costs were high, and its performance benefits remained theoretical. Many operators found it less flexible than smaller, proven locomotives that could be mixed and matched across routes. Customer reaction was swift and decisive. While initial orders were placed by major railroads such as Union Pacific and Canadian Pacific, enthusiasm faded rapidly. Follow-on orders were canceled or sharply reduced. Some SD90 MAC units were later rebuilt with conventional 710 engines, an expensive admission that the original concept had failed. For GM and EMD, the damage was significant. The SD90 MAC undermined customer confidence at a critical time, just as competition from GE Transportation was intensifying. GE's Evolution Series locomotives emphasized reliability, emissions compliance, and incremental improvement, exactly what railroads wanted. The contrast was stark. Within a decade, GM exited the locomotive manufacturing business entirely, selling EMD in 2005. While the SD90 MAC was not the sole cause, it became a symbol of EMD's strategic missteps, betting heavily on unproven technology while neglecting customer priorities. The SD90MAC stands as a cautionary tale. Railroads do not reward ambition alone. They reward machines that work day after day without drama. By prioritizing headline horsepower over operational reality, EMD delivered a locomotive that customers simply did not want and paid the price for it. Hitachi EX1200, early hydraulic series, costly reliability missteps. When Hitachi Construction Machinery introduced the early EX1200 hydraulic excavator series in the late 1980s, the company was aiming squarely at the top tier of global mining equipment. The EX1200 was designed to compete directly with large American and European excavators used in open-pit mining, heavy quarry work, and large-scale earth-moving. On paper, it represented a bold step forward for Hitachi: higher output, advanced hydraulics, and a move into a class traditionally dominated by Western manufacturers. In practice, the early EX1200 models exposed serious reliability weaknesses that proved expensive for both customers and the company itself. The EX1200 relied on a complex hydraulic system that pushed the limits of precision manufacturing at the time. Hitachi sought to deliver smoother control and faster cycle times through higher operating pressures and tighter tolerances. While this approach worked well in smaller excavator classes, scaling it up introduced vulnerabilities. Early field deployments revealed frequent hydraulic leaks, premature seal failures, and inconsistent pressure regulation under sustained, heavy loads. Mining operators were particularly unforgiving of these issues. Unlike general construction equipment, large mining excavators are expected to operate continuously for long shifts, often in extreme heat, dust, and vibration. Downtime is not an inconvenience. It is a financial loss measured in thousands of dollars per hour. The EX1200's early reliability problems quickly translated into rising maintenance costs and lost productivity. Compounding the issue was parts logistics. The EX1200 incorporated proprietary hydraulic components that were not yet widely supported outside Japan. Overseas customers in Australia, South America, and parts of Southeast Asia reported long delays for replacement parts. In several cases, machines sat idle for extended periods, awaiting specialized components, further damaging customer confidence. Hitachi's service teams responded aggressively, dispatching engineers to problem sites and issuing multiple design revisions. Updated seals, reinforced hoses, and revised hydraulic control logic gradually improved performance. However, these fixes came incrementally, not immediately. For early adopters, the damage had already been done. Reliability concerns overshadowed the machine's strengths in digging power and operator comfort. The financial impact on Hitachi was significant. Warranty claims increased sharply, and the cost of retrofitting machines in the field eroded profit margins on an already competitive product. More damaging than direct costs, however, was reputational harm. Mining companies tend to standardize fleets over decades. Losing trust at the initial deployment stage can exclude a manufacturer from future tenders entirely. Internally, the EX1200 episode forced a reassessment of Hitachi's development strategy for ultra-large machines. The company recognized that scaling advanced hydraulic concepts required far more conservative validation when applied to mining-class equipment. Subsequent models incorporated heavier-duty components, simplified hydraulic layouts, and more extensive endurance testing before release. Although later versions of the EX1200 series achieved improved reliability, the early missteps limited the model's market penetration during a critical expansion phase. Competitors capitalized on the hesitation, reinforcing their positions while Hitachi worked to rebuild confidence. The early EX1200 did not destroy Hitachi as a company, but it delivered a costly lesson. In heavy mining equipment, innovation without absolute reliability is a liability. The series demonstrated that technical ambition, when introduced faster than field readiness allows, can undermine even a well-established manufacturer's push into new market territory. Volvo EC360 first-gen electronics, innovation that failed in the field. When Volvo Construction Equipment launched the first-generation EC360 hydraulic excavator in the late 1990s, it represented a decisive shift in the company's strategy. Volvo aimed to differentiate itself not through brute force, but through electronics-driven efficiency. The EC360 introduced advanced electronic engine management, computerized hydraulic controls, and early machine monitoring systems intended to optimize fuel use, responsiveness, and operator feedback. On paper, it was a forward-looking machine designed for a more data-driven construction industry. In real-world conditions, that innovation became its greatest liability. The EC360's electronic architecture was ambitious for its time. Multiple control units managed engine output, hydraulic flow, and safety interlocks, all communicating through early-generation wiring harnesses and sensors. While these systems performed well in controlled environments, they proved far less tolerant of dust, vibration, moisture, and temperature extremes common on construction sites. Field reports quickly surfaced of sensor failures, communication faults, and unexplained shutdowns. Operators were often the first to notice the consequences. Machines would derate unexpectedly, limit hydraulic response, or trigger warning codes that disabled key functions. In many cases, the excavator itself was mechanically sound, but electronic faults prevented it from operating. This distinction mattered little to contractors facing missed deadlines and idle crews. A machine that could not work consistently was, in practical terms, unreliable. Diagnostics compounded the problem. Unlike traditional mechanical failures, electronic faults were difficult to isolate without specialized tools and training. Many Volvo dealers at the time were still adapting to software-based troubleshooting. Technicians often resorted to replacing entire control modules rather than pinpointing faulty sensors or wiring issues, driving up warranty costs and repair times. Machines sometimes returned to service only to experience similar failures weeks later. Environmental sensitivity became a recurring theme. EC360 units operating in humid tropical regions and cold northern climates experienced higher fault rates than anticipated. Wiring insulation degradation, connector corrosion, and sensor drift were repeatedly cited in internal service bulletins. Volvo issued multiple software updates and hardware revisions, but the fixes arrived gradually, not fast enough to protect early customers from disruption. The commercial consequences were significant. Contractors comparing the EC360 with competing models from Caterpillar and Komatsu found the Volvo appealing in comfort and fuel efficiency, but risky in uptime. Fleet managers hesitated to standardize on a machine perceived as electronically fragile. Resale values suffered as second-hand buyers factored potential electronic issues into pricing. Internally, the EC360 episode forced Volvo to confront a hard truth about timing. The company had pushed electronic integration faster than the industry's service infrastructure and customer readiness could support. Innovation had outpaced durability. While Volvo absorbed substantial warranty and support costs, the deeper damage was reputational. Reliability concerns lingered long after technical improvements were introduced. Later generations of Volvo excavators benefited directly from these lessons. Electronics were hardened, wiring systems simplified, and redundancy built into critical controls. Diagnostic training improved across dealer networks, but for the EC360's first-generation buyers, those improvements came too late. The EC360 did not collapse Volvo construction equipment, but it demonstrated how advanced technology, introduced without sufficient field resilience, can undermine trust. In heavy machinery, innovation only succeeds when it survives dirt, vibration, and neglect. The EC360 proved that being early is not the same as being ready. Case 580. Super L early models. Design changes that hurt trust. When Case introduced the 580 Super L backhoe loader in the mid-1990s, it was positioned as a major evolution of one of the most successful construction machines in history. The Case 580 line had built decades of loyalty among contractors, municipalities, and rental fleets. The Super L designation, promised higher productivity, improved hydraulics, and modernized systems that would keep Case competitive against rising pressure from Caterpillar, John Deere, and Komatsu. Instead, the early Super L models became a lesson in how abrupt design changes can undermine long-earned trust. Case engineers implemented several updates at once rather than phasing them gradually. Hydraulic systems were revised for faster cycle times, drivetrain components were reconfigured, and electrical systems were modernized to support new controls and safety features. Individually, these changes made sense. Collectively, they introduced complexity that early machines struggled to absorb in real-world use. One of the most common complaints involved hydraulic performance consistency. Operators reported erratic response, pressure loss during extended operation, and premature wear in valves and hoses. In applications where backhoes were run continuously, utility trenching, road maintenance, and rental use, these issues surfaced quickly. Machines that had once been praised for predictable behavior now required frequent adjustment. Transmission and drivetrain concerns followed. Early Super L units experienced shifting irregularities and accelerated wear in torque converter and shuttle components. While not universal, the frequency was high enough to raise alarms within rental fleets, where reliability across dozens of identical machines matters more than peak performance. Downtime increased, and maintenance schedules tightened. Electrical systems became another friction point. Updated wiring layouts and control modules were more sensitive to moisture and vibration than expected. Fault codes and intermittent electrical issues frustrated operators accustomed to simpler, more forgiving systems. Dealers faced longer diagnostic times, and customers faced machines that were technically functional but operationally unreliable. What damaged trust most was not the existence of problems, but how quickly they appeared after purchase. The 580 brand had been associated with durability and simplicity. Early Super L buyers expected incremental improvement, not a learning curve imposed on customers. When machines required repeated dealer visits within their first years of service, confidence eroded rapidly. Case responded with running production changes, updated components, and service bulletins aimed at addressing known weaknesses. Over time, the Super L matured into a more stable and capable machine. Later units proved far more reliable and regained much of the performance reputation Case intended from the start. However, the damage to perception lingered. Contractors who experienced early Super L issues were slower to adopt subsequent Case updates. Rental companies adjusted purchasing strategies, diversifying fleets rather than committing heavily to Case. In competitive bids, reliability concerns became a quiet disadvantage. Financially, the Super L did not destroy Case, but it contributed to broader challenges the company faced during a turbulent period in the construction equipment market. Warranty costs rose, dealer relationships were strained, and market momentum slowed at a critical time. The Case 580 Super L early models demonstrated a fundamental risk in heavy machinery development, changing too much, too fast, on a platform defined by trust. Innovation is expected, disruption is tolerated, but when customers become unwilling test subjects, loyalty erodes quickly, and it takes far longer to rebuild than it does to lose. Bucyrus-Erie walking dragline experiments, when scale crushed profitability. During the 1960s and 1970s, Bucyrus-Erie stood at the pinnacle of surface mining equipment. The company's massive electric shovels and draglines defined open-pit coal and overburden removal across North America. As mining operations grew larger and stripping ratios increased, pressure mounted to move more material with fewer machines. Bucyrus-Erie responded with an ambitious idea: walking draglines of unprecedented size, designed to dwarf anything previously deployed. Technically, the experiment succeeded. Commercially, they became a financial burden the company could not escape. Walking draglines were already among the most complex machines ever built. Scaling them further introduced exponential challenges. Bucyrus-Erie engineered draglines with boom lengths exceeding 300 feet, bucket capacities measured in tens of cubic yards, and operating weights that strained the limits of structural steel and electric drive systems. These machines were designed to walk, using massive cam and shoe mechanisms, eliminating the need for rails while allowing relocation across mine sites. The problem was not whether they could be built, it was whether they could be built profitably. Each experimental dragline became a semi-custom project. Design work, structural fabrication, electrical systems, and on-site assembly costs escalated rapidly. Unlike standardized machines, these units offered little opportunity for cost amortization across multiple sales. Every design change required new engineering hours, new tooling, and new risk. Margins shrank before the machines even left the factory. Once deployed, operating realities compounded the issue. While the draglines could move enormous volumes of material, their downtime was costly. Maintenance required specialized crews, custom parts, and long lead times. A single structural or electrical failure could idle a machine for weeks, halting entire mining operations. Customers began questioning whether extreme scale actually improved productivity when availability suffered. Power requirements also became a liability. These draglines demanded enormous electrical infrastructure, including dedicated substations and transmission lines. Energy consumption rose sharply, just as energy costs became more volatile in the 1970s. Mines that initially embraced scale began reassessing long-term operating costs. For Bucyrus-Erie, the financial exposure was severe. Contracts often included performance guarantees, placing risk squarely on the manufacturer. Cost overruns during construction, assembly delays, and warranty claims eroded profitability further. In some cases, the company spent years resolving issues on a single machine, tying up capital and engineering resources that could have supported broader product lines. Strategically, the experiments locked Bucyrus-Erie into a shrinking niche. Only the largest mines could justify such machines, limiting the customer base. When coal markets softened and regulatory pressure increased in the late 1970s, demand for ultra-large draglines declined sharply. The machines that were supposed to secure long-term dominance became stranded investments. Internally, the dragline projects distorted priorities. Engineering teams were consumed by one-off problems, while competitors focused on improving reliability, modularity, and lifecycle cost. Bucyrus-Erie's reputation for building the biggest machines remained intact, but profitability and flexibility suffered. The walking dragline experiments did not fail mechanically, they failed economically. Scale delivered spectacle, not sustainability. By pushing size beyond the point of diminishing returns, Bucyrus-Erie learned a harsh lesson. In heavy machinery, technical achievement does not guarantee commercial success. When scale outpaces market reality, even industry leaders can be crushed by their own ambition. International Harvester FEV 800 engine program, the final nail in the coffin. By the late 1970s, International Harvester was already a company under strain. Once a dominant force in agricultural and industrial equipment, it was grappling with rising production costs, labor disputes, and intensifying competition from both American and foreign manufacturers. In this precarious context, the V800 engine program was conceived as a strategic move to regain control over one of the company's most critical components, heavy-duty diesel power. The V800 was intended to be a family of large V-configuration diesel engines developed in-house, reducing reliance on external suppliers such as Cummins. International Harvester believed vertical integration would lower costs, strengthen margins, and give it greater control over performance and availability. On paper, the logic was sound. In execution, the program became a financial and engineering disaster. From the outset, the V800 program suffered from compressed development timelines and internal pressure to deliver quickly. The engine was designed to cover a wide power range for trucks, construction equipment, and agricultural machinery. That flexibility introduced complexity. Engineers struggled to balance durability, emissions compliance, and manufacturability across multiple configurations, all while keeping costs under control. Early production engines revealed serious flaws. Field reports documented issues with cooling inefficiency, uneven thermal expansion, and premature wear in critical components. Crankshaft and bearing failures emerged under sustained load, particularly in heavy truck applications. Oil consumption problems and sealing issues further undermined reliability. These were not isolated incidents. They appeared across fleets. The timing could not have been worse. Customers who had already endured reliability issues with earlier International Harvester engines were now facing another unproven design. Warranty claims surged. Dealers were overwhelmed with repairs, and part shortages compounded downtime. Instead of reducing dependence on external suppliers, the V800 increased operational chaos. Financially, the program hemorrhaged cash. Development costs ballooned far beyond projections. Tooling investments failed to deliver economies of scale because production volumes never reached targets. Each engine sold carried hidden losses in warranty support, field fixes, and customer concessions. The engine program drained resources from other divisions that were already struggling to remain competitive. Strategically, the V800 eroded trust at the worst possible moment. Fleet buyers, already cautious, began abandoning International Harvester trucks in favor of competitors offering proven powertrains. Construction and agricultural customers questioned the company's ability to deliver reliable core systems. The engine meant to anchor recovery instead accelerated customer flight. Internally, the program deepened divisions between engineering, management, and manufacturing. Engineers pushed for redesigns and delays. Executives demanded production continuity to justify sunk costs. The result was compromise. Engines shipped before problems were fully resolved. Each shipment compounded the damage. By the early 1980s, International Harvester could no longer absorb the losses. Combined with labor unrest and declining market share, the failure of the V800 program removed any remaining margin for recovery. In 1985, the company sold its agricultural division, marking the effective end of International Harvester as an integrated industrial giant. The V800 engine was not the sole cause of collapse, but it was decisive. It consumed capital, destroyed confidence, and eliminated strategic flexibility. More than any single machine, it symbolized a company trying to engineer its way out of structural decline and failing.